I have one more example here in section 1.7. I'd like to solve another rational inequality. And so we already finished example 4a. And so let's look at example 4b here. And we just need to be careful that we're following the steps that are laid out up above. This problem will be just a little more complicated at the beginning, but then shouldn't be too bad after that. So the first thing we want to do is we want to get 0 on the right side of the inequality. So the way we're going to do that is we're going to subtract the 1 from both sides. And 1 minus 1 cancels on the right. And then on the left side, we have 3 over x minus 2 minus 1 is less or equal to 0. And then we want to get a single fraction on the left-hand side. And so in order to do that, we need a common denominator. Can you see that would be x minus 2? So let's have 3 over x minus 2 minus x minus 2 over x minus 2 is less or equal to 0. And then we can go ahead and subtract. We have to be just a little bit careful here. There are parentheses around that second numerator, which is to say we're subtracting x minus 2, both terms. And so 3 minus a negative 2 gives us a positive 5, and then minus x. 5 minus x over x minus 2 is less or equal to 0. And so that gets us the form that we're looking for in step 1. So this inequality here is equivalent to the one that we started with, except now we have 0 on the right and we have a single fraction on the left. So we can go on to step 2 and we can set the numerator and the denominator each equal to 0 and go on from there. So let's do that. So in step 2, we wanted the numerator equal to 0 would be 5 minus x is equal to 0. And that would just give us x is equal to 5. And in the denominator, x minus 2 equals 0 would give us x is equal to 2. And so those are the two numbers that we'll use to create our test intervals. So if we like, we could draw a little diagram to help us see that. We can draw a number line where we label 2 on the left and 5 on the right. So we can go ahead and make our sign diagram where we have a column for interval, and then for test value, and then for the sign of the expression we're interested in is right here at the bottom of step 1. It's 5 minus x over x minus 2. And so the first interval would begin at negative infinity and go up to the first cut at 2. And then from 2 on to the next cut at 5. And then from 5 out to the right end of the number line at infinity. You might want to pause the video and try to finish the sign diagram for yourself. Test values could be 0 and 3 and 6, or they could be other numbers as well. The sign now on each of these intervals can be determined from the test value. Plug in 0 and the numerator's positive and the denominator's negative. Positive divided by a negative gives us a negative. And then plug in 3. Numerator's positive, denominator's also positive. Positive divided by a positive is positive. Plug in 6, and we have a negative in the numerator and a positive in the denominator. And so the expression is negative. Okay, so let's look back at our problem and make sure we know, were we looking for positives or negatives? Let's see. Probably best to look here at the end of step 1. This is where we wrote the inequality with 5 minus x over x minus 2 is less or equal to 0, so that would be negative. So in the sign diagram, we see that the expression is negative on the interval from negative infinity to 2. And also on the interval from 5 to infinity. And I just want to be a little bit careful here at the end, because remember, we also want to say that the expression could be equal to 0. Well, is the expression equal to 0 at x equals 2? No, actually it's not. The expression is undefined at x equals 2. So 2 is not in the solution, even though we have a lesser equal in the inequality. And then on 5, does 5 satisfy the inequality? Well, 5 makes the numerator 0, and so then the entire expression on the left is 0. Is 0 less or equal to 0? Yes, it is. So 5 gets included, even though 2 was not included. And so here is our final answer.